In our next video regarding factoring, we're going to take a look at factoring with special patterns. Now, when you take a look at y squared plus 16y plus 64, one of the things that jumps off the page at me is the number 64. 64 is a perfect square. And the fact that 8 squared is 8 times 8 is 64. And what's interesting is that 8 plus 8 is 16. So if we just go back to the first video and attack this in the same elementary method that we had set up, we said, well, 64 is positive, which means that both of these signs here are the same. This one will tell me which, so they're both positive. So I have a positive and a positive. And we go through the process of listing all the factors of 64. Right? First, taking care of our y times y is y squared. And you start thinking about 64, and you say, well, wait a second. Before I list them all out, 8 times 8 is 64, and 8 plus 8 is 16. And because we are same signs, remember, same signs equals a sum. So we're talking about a sum here. So if I just put 8 and 8 here, I think we're all set. Y times y squared, plus 8x, plus 8y, plus the other 8y, plus our 64. And when we combine like terms, we certainly get our 16y. So I think that was pretty simple. That's our final answer. We want to express that, though, in a little bit fancier version. Since they're the same thing written twice, that's going to be y plus 8 squared. And so when we take a look at y squared plus 16y plus 64, what we say is that's a perfect square trinomial. That's a great vocabulary word. Perfect square trinomial. Okay, let's try another one of those. But before you do so, just make sure you grab that last vocabulary word. All right, so here what we have again is another perfect square trinomial. But how do you recognize it? Again, just taking a look at that number 81. And 81 just stands off the page. It's 9 times 9 is equal to 81. And what happens with 9 plus 9? I get 18. So, going back to our fundamentals, the 81 is positive, which means they are both the same signs inside these binomials. This linear term sign will tell me which, so they're both a negative. W times W gives me a W squared. And I'm looking for, since it's same signs, right, that's a sum. So I'm looking for two numbers that multiply to give me 81 and add up to 18. Why, it's 9 and 9. And so we're going to express the final answer as W minus 9 squared. This third example brings us to the difference of perfect squares. Now what I see here, the difference, is subtraction means difference. X squared and 100 are both perfect squares. So what I have here is a quadratic that is the difference of perfect squares. It might be easier at first for you to see it like this. Say plus 0x minus 100. And so what we're doing is we're going to set up our binomials like always. And I see that the 100 is a negative, which means that my signs here are going to be opposite. Now, of course, x times x gives us x squared. But we're looking for, we have different signs, so different signs equals a difference. So I'm looking for two numbers that multiply to multiply to give me 100 and have a difference of 0, which means both numbers are identical. Well, 100 is a perfect square, so why not 10 and 10? And when we go to FOIL this out, x times x gives me x squared. And then you're going to get a minus 10x, followed by a positive 10x, followed by a negative 100. And when you combine these like terms, they cancel out. You're going to get x squared minus 100, giving us final factors of x plus 10 times x minus 10. Again, we call these difference of perfect squares. Take a moment before you leave the page and get the vocabulary word that goes with that example. X squared minus 100, difference of perfect squares. Okay, one last difference of perfect squares example, and so again, just an alternative way of thinking about it. I don't really want to formally write it this way, so the white will be the way I think about it, is I have a 0t, that linear term, right, is 0. So when I'm thinking about the splitting of my binomials, that 9 is negative, so that's a plus and a minus. And t times t gives me t squared. And two numbers that multiply to negative 9 and have a difference of nothing. Again, meaning that the numbers must be the same. So 9 is a perfect square. So that's 3 and 3. And when you FOIL this out, you're going to get t squared minus 3t plus 3t minus 9. Those cancel out, and you're left with t squared minus 9. So t plus 3 and t minus 3 are our factors, and prime at that. You might ask yourself, where are we going to take this factoring business, Mr. Brecklin? Well, we're going to solve quadratic equations, but first you need to learn to factor in order to solve quadratic equations. So for the first time now, you're going to start bumping into multiple solutions, not just one solution like in linear equations. Quadratics have the possibility of having two, one, or no solutions. In linear, you would just have one solution, no solution, or infinite solutions. So let's try this out. What we're going to do is the first thing we'd always like to do in solving quadratics is set the equation equal to 0 if it's not already. This one's already all set up. So what we're going to do is just focus our attention on the left side. We're going to factor the left side. That 63 is negative, so we're going to have a plus and a minus. R squared is an R and an R. Factors of 63 that have a difference of 2 is going to be 7 and 9. So the 2 is a positive 2R, so 9 is my bigger number because the difference, remember, these are different signs, so we're talking about a difference. If two numbers have a difference of positive 2R, then the larger one, that 9, must have been the positive number, and the 7 is negative. Now what do we have here? We have our A times B equals 0, and we've talked about this in class before, that either A or B must be 0. So we're going to take both of these. R plus 9 equals 0, and R minus 7 equals 0. And R is equal to negative 9 here, and R is equal to positive 7 here, so R is equal to negative 9 and 7 respectively. And those are our two solutions to this quadratic function. Now if we were to draw a graph of this equation, right, and change that 0 to an f of x, this would be a quadratic equation, or I'm sorry, a parabola opening up because our coefficient of the quadratic term is positive, and negative 9 and 7 would be our x-intercepts respectively. This is a lot of stuff that's starting to come together. So as I said previously, in solving quadratic equations, we want to set everything equal to 0 first. So as you notice, this one is not set equal to 0. My y squared over here by itself. Now, although it would be easier to just move the y squared, I would make y squared negative, and that's going to complicate things for you guys. So what I would suggest is keeping that coefficient of the quadratic term positive, which means instead of moving the y squared, I'm going to move both of these terms. So I'm going to add 3y to both sides and subtract 28, right, using inverse operations, and I get 0 is equal to y squared plus 3y minus 28. Okay, just simply setting everything equal to 0. Now I'm going to focus on the side that can be factored. So I'm going to split up my two binomials. I have a negative 28, so that means this is a positive and a negative. I have a y squared, so it's a y and a y. Two numbers that multiply to give to 28 and have a difference of 3. That's going to be 4 and 7. The difference, right, because this is a difference, different signs means that this is a difference right here, right? Positive 3y is the difference of two numbers of 4 and 7, so 7 must be positive, 4 is the negative version, right? When you go to check foiling these two binomials, we get a plus 7y here and a minus 4y. That's going to give you a plus 3y difference. So we're good to go. Now we're going to take our two binomials. Remember that a times b equals 0. So they one or both must be equal to 0. So I set them equal to 0 independently. Y plus 7 equals 0. Y minus 4 equals 0. When I subtract 7 and I add 4 to both sides, I get answers of y equals negative 7 and positive 4, respectively. And those are the x-intercepts to the parabola that is described as y squared plus 3y minus 28. One last one. Okay, first thing I see here, it's a quadratic, but it's not set equal to 0. So I'm going to subtract 121 from both sides. And even though I have the 121 that's written in front of the a squared, I can't write it underneath it, and I didn't want to squeeze it to the right and make things garbly. I am going to write the a squared first, though. So that's a positive a squared minus the 121 equals 0. Difference of perfect squares, I notice right away 121 is 11 times 11, so that's going to be a plus 11 and a minus 11 equals 0. And set each one equal to 0, so a plus 11 equals 0, a minus 11 equals 0, and I'm going to get a is equal to negative 11 and positive 11 respectively, or a is equal to plus and minus 11. That's it. You should be good to go. Now you possess all of the skills necessary to complete on page 256 numbers 15 to 35, which we will also work in class, and you will finish for homework. So again, I suggest a jump start.